let's start talking about this one. Again, my first strategy is usually to draw my max and my min and figure out where the max and the min are for these. Typically, they'll give you some information about that. What'd you get for the minimum value? How low does this yo-yo go? 5 inches above the ground. And how high? Up to the string length is 30 inches, so that would be 30 inches above there, which would be 35. And it's usually helpful to know where the midline is because that would typically be at the x-axis if it hadn't been vertically shifted. So wherever that midline is going to help us find our vertical shifts. We also should know what's going to be in front of our function here, which would be our amplitude. That would be vertically how far to go from the center to the top or the center to the bottom, which is 15. We got 15 here and 15 here. So our amplitude is 15. We need to figure out what our period is. We need to decide on sine or cosine, and then we need an omega. So we're most of the way done with this problem already. Where does the yo-yo start at time 0? Top, bottom, center? At the bottom. It's going to start down here. And then it's going to swing up and then eventually return to that original position again. And how long does that take? 2.5 seconds. So, all right. So when you look at that, does that look like a sine or a cosine to you? Cosine, positive cosine, or negative cosine? That looks like looks like a cosine has been flipped over. So we'll go ahead and put a minus in front of that 15. And all we need here is omega. We've got t, so that shouldn't be too terribly difficult. T is 2.5, so 2 pi over 2.5. One of the big rules in math is we don't need fractions inside of fractions. And decimals are fractions, so that's not going to fly. We'll need to modify that. Can you think of a fancy version of 1 that I could multiply by here so I would no longer have a decimal on the bottom? 2.5 times 2.5 is still going to leave me a decimal in there. What can I multiply anything with a 0.5 by? How about 2? Yeah. Times 2 would give us 5 down here. That doesn't have a decimal in it. That should work. Let's multiply by a fancy 1. 2 over 2 to get omega that would be 4 pi over, which is nice and reduced and does not have any decimals in it. And that should be it. Now we should be prepared to answer questions about things like when does it reach the maximum heights? We probably don't even need a calculator for that. How far into its period is it going to reach its maximum height? Halfway, and the period's 2.5 seconds. So half of 2.5, 1.25. 1.25 seconds. But we should also be prepared to answer questions like, when's the first time that it will be 21 inches above the ground? And in that case, we'd want to use our calculators. If we had time on the exam, even if they didn't ask us follow-up questions, it would probably be a smart move to graph this and see if we're getting the correct graph our equation. Let's go ahead and practice that right now. And give us an opportunity to practice setting up a window. Remember, that's really key. You should be setting up your window before you even type in the equation. If I can get you guys to develop that habit when you're doing these kinds of graphs and calc, that you can get your window set up before you even type in your equation. That would make your future calculus teachers very, very happy. So you need to think about how much you want to show in the x direction. I'm going to make mine go from 0 to, what do you think? You want to just do one period? We did last time. Let's do 2 periods. Let's branch out a little bit today. Let's graph 2 periods. How far out would I need to go to get 2 periods? I need to go out 5, right? 2.5, another 2.5. I'm going to make mine go out to 5. Why not? And then the y direction, you could just go from 5 to 35. I like to go a little bit below, a little bit above. I think I'm going to go 0 to 40. Maybe I'll make mine go by 5s because all the important stuff happens in multiples of 5. And then I'll type in my equation and graph it. Hope that I see what I expect to see. What do we have? And if I graph it and I get like a pretty flat horizontal line, I'm not going to freak out. What did I forget to do if I graph it and I get a flat horizontal line? It's the first thing I should check. Yeah, check your mode, make sure it's in radians. I can already see on my screen that my calculator is in radians, but just know that that happens sometimes. You mess around in degrees, you go to graph a sine or a cosine, and it just doesn't look right. Before you freak out and think you did something wrong, check your mode. Make sure you're in radians. So, yeah, it's looking pretty good. It finishes right at the edge. Oh, yeah, that's definitely the right equation. All right. Okay, any questions on that one? Moving right along. Second question is about a dump truck. Giant wheel, 64-inch wheel. 64 inches. That's a little bit shorter than me. That's a big wheel. That must be a big truck. Yeah, it must be one of those giant ones they have like at the quarries and stuff. Do you really? Wow. I've always wondered how much the tires for those things cost. I mean, a tire for a car is like $70. But oh wow. All right. So this one's about a truck wheel, and this wheel, this tire on this truck is going to turn not a full revolution, and we got to figure out how far is the truck going to move when it rotates through this angle. So kind of the trick to this is to recognize that when a wheel rotates, the edge of the wheel is going to come into contact with the road. So if a wheel rotates one full revolution, how far is the vehicle going to move? One circumference was the answer I was looking for. It would move one circumference, whatever the circumference is, right? If you wrapped a tape measure around a wheel and you found that it was 6 feet all the way around the wheel, if you pushed that wheel through one revolution, you would find that that wheel moved exactly 6 feet. Because basically every point on the edge of the wheel is going to come into contact with the ground till it gets all the way around. And it's kind of like you're wrapping that distance along the ground just along the edge of the wheel. So what we're looking at here really is they're asking us for a portion of the circumference. When I read this problem, I was like, this is an arc length. They're asking us to figure out a small part of the circumference. Well, not small, it's almost the full circumference, right? 360 degrees would be the full circumference. We just want to find a piece of it. So, how are we going to proceed here? Something about the circle, find the circumference. That could be useful to us to know what the whole circumference is. That makes me think of, I'm talking about parts of circumferences and whole circumferences. What does that make you think of? What's that thing that starts with a P? We've done a couple of problems with this. It's a type of equation that has a fraction on both sides. You remember what those are called? These are all really good math vocab terms. They start with P, but I haven't heard the one that I'm looking for yet. A proportion. And we solve proportions by doing, this is the important thing. How do we solve proportions? How do we solve it? Once we get it all set up, how do we solve it? Cross multiply. Yeah. Okay, so that's what it makes me think of. I think you're on the right track. I think we probably need to figure out what the whole circumference is. We certainly have enough information to do it. We've got the diameter. The circumference of a circle, do you remember the formula for that? 2 pi r or pi d. So this time, since we have the diameter, I'm going to go for pi d. So the circumference is pi times 64. That would be 64 pi. That's going to go in one of our fractions. Now, is that the whole thing or the part? Whole thing, which we typically put on the bottom. There's no like set rule about that, but typically the whole thing goes on the bottom. You want to go left or right? No wrong answer here. All right. Okay. Sorry, I heard a couple rights before. I heard some lefts. So 64 pi on the bottom. What should go above that? X. Heard X. This is circumference. I want to keep this fraction with just circumference. If this is the whole circumference, would X be the part of the circumference that we're looking for? Yeah, that's what we said we were going to try and figure out the portion of the circumference that would result from this. So I'm going to put an X up there. Now you talked about 360 degrees. That could be in my other fraction. Would that go on the top or the bottom? Bottom, because it's the whole thing. Jack, you got a question, comment, concerns? What about on the top? 280. Yeah, okay. So cross multiply, solve that thing, and we'll get our answer. I'm gonna guess it's less than 64 pi. It should probably be less than 64 pi, right? 64 pi is around 180, 200, something like that. And that's gonna be about 3/4 of that. So I'm gonna guess we're looking around 150-ish, 140, 150. All right, so 360x. So what we just found was the distance around the edge of the circle going through 280 degrees. So another example, proportional reasoning. Again, these things tend to come up quite a bit in calc. If there are no questions, we'll go ahead and move on to number 10. Go ahead and have a read through that. There's a lot of information in number 10, and yeah, you're going to kind of get used to this. And math professors write tests and math teachers write tests. We're not always the best writers. English, we don't practice reading and writing essays all day like English teachers. So sometimes you might have to read something 3 or 4 times to figure out what it is that they're trying to communicate. I would say read through number 10 and try and make a sketch. Let's just start with that and figure out what the heck are they even trying to describe here. Now, this is the type of problem that if you have never watched a baseball game in your life, if you have never stood on a baseball field, you're going to have a hard time with something like this. It's okay to ask your teacher or your professor, let them know, like, I don't know anything about baseball, and let them draw you a picture of a baseball diamond. It's okay to ask for that, okay? So for just in case anybody here is in that position, a baseball diamond, it's a square. Oh my gosh, that's a terrible square. And there are bases at the 4 corners. Well, 3 of the corners, and then home plate at the 4th corner. And these are bases, these are not angles, because they're not always exactly 90-degree angles. Depends on the field. And then this would be called the infield. Typically, there's a lot of dirt in the infield because they do a lot of running around, and it would destroy the grass. And then the outfield is typically grass. This is where you hit the ball onto. So this would be the dirt that they're talking about. And then this out here would be the grass, the outfield grass. And so this problem is describing a sprinkler system that they're going to set up, and the goal is to water the outfield grass without getting the dirt all wet. And what we got to figure out is what's the area of this thing that's getting watered. All right. So you get the idea of what they're asking us for, sort of. So I'm going to redraw this, and I'm going to take out the baseball diamond and everything. Really, we're looking at a giant slice of pizza, aren't we? Yeah. Someone took a real bite out of it. All right, so we're looking for the area of this thing right here. And we have some information that's going to help us do this. We have an angle. They told us what our central angle would be. It's 100 degrees. Oh, you know, I should label this too. They mentioned the wall. The wall is on the outside. So the dimensions that they're giving us in feet are, they say the distance from home plate to the outfield grass. So that would be this dimension here. So from home plate to the outfield grass is 127.6. Put that on here too. And the distance to the outfield wall is 380 feet. The challenging thing is to read through and figure out, okay, where do all these numbers go? What am I looking at here? And then start coming up with a strategy for solving. So we've dealt with a couple problems that involved sectors. Sectors is like the pizza slice. This is definitely a sector, except it's a sector with the chunk taken out of it. So what's our strategy going to be? Yeah, kind of like exactly like if it was a piece of pizza that someone took a bite out of it. Find the area of the whole sector. So my strategy would be, let's find the area of this whole thing. And then let's find the area of this piece that we took a bite out of. And we'll subtract those two things. And whatever's left over should be the leftover part of our pizza. So we need to find the area of two sectors. They both have the same angle. One has a radius of 127.6 and one has a radius of 380. So if I were working this problem, I'd probably start dividing my work section up into a couple spots. We got a smaller and a larger sector. We're going to need, since we're talking about area, we're going to need to find the area of the whole thing, like the whole circle, the whole pie that this sector was cut out of. So I'm going to go ahead and do that. For my smaller one, it would be, well, it's pi r squared, so pi times 127.6 squared. And for the larger one, it's still pi r squared, but r is now 380. Both of them have an angle of 100 degrees. I think we should be pretty good to set up and solve a proportion. Some of you might be tempted to type that into your calculator and get a decimal answer for it. You can do that if you want. I'm just going to leave it as is. And I'll just stick that into my proportion. That was the whole area. I'm going to put it down here. Pi times 127.6 squared. No, I'm just focused on this little guy for right now. And then I'm going to come back and do the other one with the 380. So when I say the whole, I'm actually talking about the whole circle that this thing was cut out of. And I know I need to find that because I know the angle of the slice, and I know the angle of the full circle also. So that's why I know I needed to come up with the area of the whole circle. So the angle of my slice was 100. The angle of the full circle, if we were to make a whole circle out of that, would be 360. And I'm going to call this the smaller one. I'm going to call it 8. The area of just this sector. Yeah, and there is a formula for that. Yeah, there's a formula for the area of a sector. You have to have your angles to be in radians. It's we figured this out yesterday too. It's 1/2 r squared theta, if you're interested. A1 is going to be the area of the slice. Oh. This is going to be the area of the whole circle that the slice was taken out of. Yeah. 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 A1 is going to be, yeah, A1 is going to be my little small area here. I could call it X. I figured I would call the smaller area A1 and the bigger area A2. And then eventually we're going to do A1 or A2 minus A1, and that'll get us our final answer. Yeah. Yeah, that's a little confusing. My apologies. So I got 360A equals 100 pi times 127.6 squared. And here's where I'd reach for my calculator. Type in 100 pi times 127.6 squared divided by 360. It's a lot. It's a big number. It's a little shocking to me at first. Are you guys coming up with a big number like 14,000? Man, that's the area of the small piece. The area of the big one's gonna be a lot bigger. Let's go. Let's round a whole number, I guess, if we're dealing with numbers that big. But you think about like the size of a home, right? Two-family homes are typically between 1,000 square feet and 2,000 square feet. So, you know, a big two-family home would be like 3,000 square feet. So, if you think about the infield of a baseball field, you could stick several houses in that area, right? So, yeah, yeah. Anybody know how many square feet there are in an acre? It's like thousands. I don't know. All right, let's do the other one. It should be the same setup because it's still 100 degrees. I'm gonna call it A2 this time. And I think this time I'm just gonna jump straight to my final answer. I'll end up multiplying this time this and dividing it by this. So are you guys okay with me skipping steps? Does it bother anyone how like we've transitioned you from algebra 1 where we yelled at you for skipping steps to pre-calculus where like, yeah, let's just type it straight into the calculator. Does that bug anybody? No, I don't. Yes. So that's an important place where you don't want to skip steps, and I try at least once in the notes. I try and show the full steps, right? But I get you. I've been there before too. Wow, 126,013. Yeah, and these are square feet. And I think we just subtract those, and we're done. That's the whole circle would be pi times 380 squared.
And that's 900,000 roughly.
Woo. That's way bigger. Yeah. 453,000. 500,000 square feet. All right, then we subtract those, and I think we're good to go. And the answer that I'm coming up with is about 111,800. I'm just going to say 111,800 square feet. We're talking about a sprinkler system here. I don't think that extra 4 square feet is going to make a difference. I am curious though. How many square feet are in an acre? Let's ask Google. I guess in 20, go up. a little below. 43,000, 43,500 basically. 43,560. 43560. So we're looking at what? That's like how many acres? 111,000. 1 acre is about 43,000. Two would be, yeah, under 3, about 2.5-ish. Does that seem reasonable? Anybody have a yard that's about 2.5 acres, 2.5 acres? Yeah, I think it makes sense. It seems reasonable to me. It's a big number, but it seems reasonable. Okay. I'd be happy to go over any questions you had from the book review. There are now 3 exam reviews out of the textbook listed on Canvas. I really hope that you will work through all of them and ask questions about them. We've got the rest of this period today, and then we've got Monday. Yeah. Would anybody like to go over anything from the exam review from the textbook? Oh, I had a lot of fun with this one a couple days ago. Yeah, I'm gonna give you a hint on this one. If anybody hasn't done this problem, save yourself some headache, please. Can you get those phones put away? Let's focus here. So page 497. This is number 6, and it's a verify question. And it's cosine squared x. No, it's not. It's cosine squared of 2x, which is what threw me, minus cosine squared of x equal to sine squared x minus sine squared 2x. And I went round and round with this. I tried starting on the left. I tried starting on the right. I literally have, I think I recycled it, but I have like 4 whole pages of like me screwing around with this thing, trying to do it. And I should have just stopped and walked away from it and come back to it. All right. Here's the tricky thing about this. Okay. You see that 2x in there, you think you got to use double angle identities, right? That was my assumption. When I see a sine or a cosine of 2x, and especially the sine 2x, because this comes up a lot, I thought I was going to end up using this thing. You don't. This entire problem is Pythagorean. Pythagorean is all you need. You need to know that sine squared of something is equal to 1 minus cosine squared of something, and the cosine squared of something is equal to 1 minus sine squared of something. That's it. So I'll give you a hint for your first move. Just replace the cosine squared of 2x with what? I would replace this with 1 minus the sine squared of 2x. Sine squared plus cosine squared is equal to 1. So cosine squared is equal to 1 minus sine squared. And replace your cosine squared x with 1 minus sine squared. And then suddenly it becomes a 2-step identity. I think you distribute the negative and rearrange the terms and you're finished. I struggled so much with this one, and I'll be honest, I didn't figure it out on my own. I had to crack open the solution manual. I got too frustrated. It's taking up too much of my time. All right, I'll let you finish that one off, but yes, if you spent a lot of time on that one, I feel your pain. Yes. Yeah. Oh yeah. It is time. Library trip for the seniors. All right, what else do we do from the bookwork? Thank you for that one. I'm glad to know I wasn't the only one who struggled with that. 29, give me page number.
439.
439, thank you. 29, you said? 30.
No, but number.
439, number 29. I'm with you.
Yeah.
We got it. 29. Right, evaluate exactly all 6 trigonometric functions for the angle. Use reference triangles for the calculator. All right, so 29, we got negative pi over 6. So, is this the right one? How do we want to do this? So this was back before we had a unit circle. If they asked me to do this and they didn't tell me specifically to use reference triangles and I would use the unit circle, I wouldn't be drawing reference triangles. If something like this were on the exam, you would probably use unit circle rather than reference triangles. So are you okay with us doing this with slightly different from the instructions? Because that whole section of the chapter 4 was to kind of help us start wrapping our heads around this unit circle. So let's do it the unit circle way. So negative pi over 6. What I'm going to do is I'm going to actually focus on positive pi over 6 for right now, and then I'll use odd and even to modify it. Okay. So basically, I'm going to find the sine of pi over 6 and the cosine pi over 6 and the tangent of pi over 6. Actually, you know what? Let's just do the negatives because we can find the negative on a circle. So if I'm looking at my unit circle, I know that positive pi over 6 is right here. So negative pi over 6 would be the same angle, but in the opposite direction. It'd be right here. So well, here's my cosine and there's my sine. So the cosine of pi over 6, negative pi over 6 is radical 3 over 2. The sine of negative pi over 6 is negative 1/2. So radical 3 over 2. And, oh, I got that backwards. The cosine was radical 3 over 2 and the sine was negative 1/2. And tangent we know is, we can build tangent with sines and cosines. Which one goes on the top? Tangent sine over cosine. So if I did 1/2, negative 1/2 over radical 3 over 2, the over 2 parts would cancel. I could also think of multiplying by a fancy version of 1, multiply by 2 over 2. That gets me just negative 1 over root 3, which I wouldn't really have a problem with, but for those of you who are not taking the CWU exam, that will never be, that's not going to be one of your options. It's multiple choice. So one of the things that we got to get used to with multiple choices, like that is a correct answer, but they would rationalize this as the answer on. So you would not see this as one of your options. You need to know that that is the same as negative root 3 over 3. That's the rationalized version of that. Do we need to go through how to rationalize negative 1 over root 3, or do you guys remember how to do that? You just multiply it by a fancy 1. My fancy 1 would be root 3 over root 3. So we've got 3 of our trig functions now, but we're on easy street. Because to find the other 3, we just need to take reciprocals of these things. So if sine is negative 1/2 and cosecant of the same angle would be negative, and then reciprocate it. 1 over 2 becomes 2 over 1, aka 2. The secant would be, take the reciprocal of radical 3 over 2. It's now 2 over radical 3, which again, we're not going to see that listed as a possible answer. We need to rationalize that. That would turn out to be 2 radical 3 over 3. And the cotangent, I could take the reciprocal of any version. I think I'm going to take the reciprocal of this version, and I won't have to worry about rationalizing it, right? So that would be negative radical 3 over 1, or just negative radical 3. Throughout these, the reviews that you're doing out of the textbook, if you see some instructions, you're like, well, this would be way easier to do if I use the unit circle, or this would be way easier to do using law of cosines. Feel free to use, you know, I'm not going to tell you how you have to solve stuff on the exam. So if you've got if there's another tool that we learn in a later chapter that would make a problem simpler, then practice it with the best tool. Bend the instructions to give yourself good practice is what I'm trying to tell you. Anything else from the reviews assignments that we can talk about? Thank you. I guess not. Yeah. So number 30 is the same idea. If they give you 19 pi over 4, and that's not on our unit circle. So yeah, what can we add and subtract and get the same, end up in the same position? We can add and subtract a full circle, since this is in radians. So what I would do is I would just subtract 2 pi from it a bunch of times until it did end up inside the unit circle. So I'm going to do minus 2 pi from it. Now, I'm not going to do 2 pi. I'm going to think of it as something over 4. 8 pi over 4, that is the same as 2 pi, isn't it? That's way easier because it has a common denominator. So 19 minus 8 will get us to 11. That's still too big. Minus another 8 will get us to 3 pi over 4. For the practice assignments, I do not. There's no solutions on Canvas. The odd numbered problems have answers in the back of the book. If you need even numbered problems, just ask me. We can look at the solution manual. If you've already done a bunch, you're welcome to. I'll set the solution manual up. You may not take photographs of the solution manual. That is like a major copyright file. If you wanted to look at them, that's okay. All right, any others? All right, stop this.